Can you go please?
Okay, I'll share my screen. How's this? Can you see?
Yes. So you have 15 minutes and 5 minutes for questions.
Okay, hello. My name is Duncan Mays. I'm from Queen's University in Canada, and I'm here to you today to present our work on decentralized data allocation via local benchmarking for parallelized mobile edge learning. To start with, I'd like to thank my co-authors, Sarah El-Sayed and Hassam Hassaneh. We call our method DAB, and it's a method for parallel learning on heterogeneous edge devices. DAB uses benchmarking to assess device capabilities, and then it intelligently allocates data between them in order to preserve synchronicity and eliminate update staleness. The Internet of Things is coming. Studies find that by 2027, 41 billion new devices will come online, generating an additional 800 zettabytes of data, 90% of which is too latency sensitive to transmit to the cloud for processing. Thus, mobile edge computing has emerged as a paradigm to process this massive amount of data at the edge and thus avoid the need to transmit it long distances, which reduces network load and latency. Deep learning has found itself at the heart of many applications for mobile edge computing. Speech recognition, object detection, and text completion all depend on neural network models. Moreover, the data-intensive nature of training deep learning models motivates this training to be done at the edge of the internet. And so parallel learning is a training regime which can harness distributed compute in edge devices. In parallel learning, a single orchestrator will recruit a set of distributed learners and send a subset of its data to them. Each learner will then independently and in parallel train a neural network model on this data that's allocated to them. The parameters of the models on each of the learners is synchronized periodically via averaging, but this can only happen once all workers have completed their training regime. And so it's important that all workers finish at the same time so stragglers don't slow down the process. Device heterogeneity is a major issue in parallel learning, and it contributes to this straggler problem. Device heterogeneity refers to differences in learners' computational and communicational capabilities, as well as in their willingness to participate. If the orchestrator were to send the same task to each learner, it would be limited by the weakest one. And so the orchestrator needs to have some way to assess the capabilities of each device. In the past, this has been done by benchmarking, usage monitoring, and prior knowledge of hardware. Past works that have dealt with heterogeneity do so by adjusting the size of the task that's given to each learner. And this is done so that all learners will finish their task at the same time, regardless of their capabilities. Methods to do this fall into three broad categories. Firstly, methods that change the size of the model that's trained by each learner, methods that change the number of iterations that each learner performs, and methods that change the amount of data that's allocated to each learner. HeteroFL was one such method that dealt with heterogeneity by changing the size of the model given to different devices. And so weaker learners were given smaller models that they could train at the same speed as stronger workers with larger models. This came with the disadvantage that it was very computationally intense for the orchestrator, since creating models of different sizes was done via parameter tuning or pruning. Another method to do so was to allow workers to perform different numbers of learning iterations. And so faster learners could perform more iterations and therefore deliver more potent updates. But this came with the disadvantage of parameter staleness, which is a metric of the differences in the number of iterations on each update. Now, parameter staleness correlates with loss, and so is usually avoided when designing parallel learning algorithms. That said, some works have found that accepting some staleness in order to take advantage of stronger workers is advantageous in the long run. This last point is important. It explains some of the results we'll get. Large gains in parallel learning have been made by changing the amount of data that's allocated to each learner. So weaker learners would receive smaller subsets and stronger learners would receive larger subsets. This has the advantages that it's not computationally intense for the orchestrator, and it has the potential to completely eliminate staleness. Due to these advantages, this was the method that we chose in our work. And so in DAB, all learners perform the same number of updates on the same model and are differentiated in the size of the data subset that's allocated to them. Now, past work that has done this has assumed a prior knowledge of the learner's computational capabilities. And this is a poor assumption in many environments. Learner capabilities can change over time, or even the learners themselves can join or leave the cluster. And so we need a way to determine the capabilities of each learner. Training neural networks is a mostly mathematical operations, and so floating point operations per second, or flops, is a metric that's emerged to characterize the training ability of GPUs. Backpropagation speed is known to have a really complicated relationship with hardware properties, and so flops-based methods are used in lots of research, but have been shown to be very inaccurate. The current state of the art in performance prediction for deep learning is called Habitat, and it works exclusively on PyTorch models with CUDA-enabled GPUs. Habitat is very accurate, it's effective, but it's very specific in scope and it's very complex. And so implementing it for a generic system would require many work hours from skilled developers, and this just isn't accessible to the average researcher. In contrast, our method is extremely simple and can be readily implemented for any model architecture and hardware. Our method is called subset benchmarking because it runs a subset of the task and times it, and then it extrapolates the runtime of the whole task from the runtime of this subset. Workers will begin by obtaining a training deadline D from the orchestrator, and this is the amount of time that they have to complete their local update. They will run two benchmarks, CK and BK, and then they will calculate their upper bound, which is the maximum amount of data that they can train on in the given amount of time D. After this initial stage, the training algorithm will commence. And the training algorithm is consisting of many global update cycles, each of which involves the following three steps. Firstly, learners will download data shards and model parameters. They will execute some training iterations, and then they will upload their trained parameters back to the orchestrator for averaging. Global updates are repeated until the neural network converges to the desired accuracy. And it's important that each learner is allocated just enough data that it takes them D seconds to process it so that there aren't any stragglers holding up the process. With respect to the benchmarks, CK represents the number of data shards per second that the learner can download. So it's the communication capability of the learner. And it's done by just downloading a certain number of data shards, timing it, and then dividing the number of data shards by the amount of time it took to download them. BK likewise represents the number of shards per second that the learner can train the model on. So it represents the computational capabilities of the learner, and also involves training the model on a certain number of data shards and then dividing the number of data shards by the amount of time it took to train on them. Given these benchmark scores, we can then calculate the amount of time it should take each step in a global update to take. And then given these equations, we can solve for the maximum amount of data that the worker should be able to process in the given amount of time. Given this upper bound, the learners can then inform the orchestrator on the amount of data that they'd like to train on. Now, this sort of decentralized allocation scheme is tolerant to learners who don't want to dedicate themselves completely to the training process. So learners who aren't willing to participate fully can request an amount of data that's less than their upper bound, and the algorithm will proceed as normal. And so this allows for workers who don't want to dedicate their whole training resources. We evaluated our benchmarking scheme separately from the training regime, and we did this relative to a flops-based method from citation number 11. Now, across the board, subset benchmarking outperforms flops, but at best, with the largest benchmarking size of 8 shards, subset benchmarking showed an 83% reduction in prediction error as compared to flops. And this is runtime prediction error for a training loop. Subset benchmarking outperforms flops because training neural networks has lots of bottlenecks other than the rate at which the device can perform floating point operations. And subset benchmarking doesn't bother modeling the computation, it just runs it and times it. Now, some limitations of subset benchmarking are that its accuracy depends on the benchmarking size. Small benchmarks might not be very accurate. Moreover, results reported from subset benchmarking are specific to a certain model and device and cannot be used to make predictions for the same model on a different device or a different model on the same device. For our training regime, we conducted experiments on a feed-forward neural net on the MNIST dataset with the following configuration of ReLU activation, categorical cross-entropy loss, and a shard size of about 500 samples, or well, actually exactly 500 samples. Now, the hardware we ran experiments on consisted of several Raspberry Pis, as well as a Jetson Nano and an RTX GPU. And we didn't use a simulation. We actually ran this on real hardware. As a transport layer, we used our own homegrown RPC framework, Axon. This was developed at Queen's as an educational tool. And while it isn't as fast or efficient as gRPC, it is very easy to use. You can install Axon from pip, or you can look at the code on my GitHub page. The method we chose as a baseline for data allocation is a staleness-aware scheme from citation 6. And what I mean by staleness-aware is that it allows some staleness in order to take advantage of stronger learners. It was a centralized allocation scheme, and it used an optimization formulation, and we'll refer to this as CSA. We ran experiments on 2 clusters of devices. The first cluster consisted of only 2 devices, a Pi and a Jetson Nano, and the second cluster had 4 devices, three Raspberry Pis and the Jetson Nano. The figures on the right show the loss and accuracy of the neural network trained with DAB and CSA across varying global indices on the first cluster of 2 devices. We can see that DAB closely approaches the loss and accuracy of the baseline, despite being a decentralized allocation scheme that allows for workers who don't want to participate fully. And upon convergence, DAB was only around 2% lower than CSA. DAB performs well because workers can train on the maximum amount of data that they can process in the given amount of time. But CSA still has an advantage due to its staleness awareness, because it can allow workers to perform a different number of learning updates. And past research, this lines up with past research. Now, the figures on the right show the loss in accuracy of neural networks trained with DAB and CSA on the second cluster of 4 devices, so 3 Raspberry Pis and 1 Jetson Nano. And we can see that while DAB pulls ahead in the beginning, its converged accuracy is lower than CSA. In the beginning, DAB was at global index 1, DAB had an accuracy 18% higher than CSA, but upon convergence, it was 7% lower. Now, this is because DAB pulled ahead early in training because it doesn't imply any bound on the amount of data that each learner can get. Each learner processes the maximum amount of data that they can in the given amount of time. And so DAB had a higher data throughput than CSA, but it didn't perform as well as CSA on converged accuracy because of this staleness awareness in CSA. Now, CSA could better exploit the Jetson Nano. It put more weight on the updates from it, whereas in DAB, the updates from the Jetson Nano were watered down by the updates from the Raspberry Pis, and so DAB didn't converge to the same accuracy as CSA. So in conclusion, DAB did not outperform our baseline. Neural networks trained with DAB are not more accurate than networks trained with another method. In my opinion, the most valuable contribution of this research is subset benchmarking. Determining the speed at which a device could train a neural architecture was an open issue in parallel learning research, and subset benchmarking is a really simple and effective method to do so. Thank you for your time. Are there any questions?
Thank you. Thank you very much. Any question?